Right, I just wanted to give you some tips on getting started with this. Um, and you don't have to do it today, but when you have time to get started, I wanted to just help you make it a little bit easier. So basically, the picture that they're showing and the description that they have is you got this airplane, and it starts out at some altitude h, and the distance away the distance it's away from where it's going to land, which is right here, is L. So L is our X is our horizontal distance and Y is our vertical distance. So they describe the path as this curve right here, and they're using P of X to describe that. That's just really your Y value. Just keep that in mind. That'll be easy. They'll make things easier when you get going to remember that that's just Y. And so there's a couple things that they tell you. They're saying that the horizontal velocity of the airplane is constant and it's equal to v. And the airplane's going to the left. So we won't use this for quite a while, but the velocity then is actually minus v because it's moving to the left. That's why it has the negative sign. Going to the right would be positive, going to the left is negative. And just remembering that the velocity is the derivative of the x position with respect to time. This is in the x direction, and that's why it's the derivative of x, because the velocity is the x velocity. Another thing is that the acceleration that they're talking about, the plane can't have acceleration bigger than some value k. That acceleration is in the y direction, and that's going to be the second derivative of y with respect to time. And we'll come back to that in a little bit. But those are just two things that they're describing. So they're saying that you want to describe the curve by this cubic function. And basically, your first job is to try to figure out what all these constants are. The constants you have to figure out what they are A, B, C, and D. Because you want to write them in terms of things that you know about the problem. You want to be able to write them in terms of H, L, and V. And then it could have constants as well. Sometimes it gets confusing when you don't have numbers, but you view these things as things that you're given, so they're like your knowns, and you're trying to express these things, which are unknown, in terms of those constants. And the first thing that they are describing in the problem, the conditions, those are things that are going to actually help you figure out what all these constants are. The first two things are that you can actually see what the value of P is at the two different values of X. When X is 0, the Y value is 0. And the other thing that we know is that when X is equal to L, the Y value is H. So we're going to use these two conditions to try to figure out what some of these constants are. So if we let x equal to 0, and we're going to set that equal to 0, the first three terms just disappear, and we're only left with d. So right away that tells us that d is 0. And so that's kind of nice. We can get rid of that right away. Now using this, we'd have P at x equal L is equal to H. We're going to get A L cubed plus B L squared plus C times L. Right now that's not terribly helpful, but we might come back to it and be able to use it in a little bit. The other two things they told you is to think about the derivative of P of x, which is really just the slope of the curve. And if you notice, at the very beginning and at the end, the slope of the curve is 0. So this is 0 at x equal L and at x equals 0. And that's our other two conditions that we're going to use to help us figure out some constants. So first of all, let's find the derivative. And that's 3ax squared plus 2bx plus c. And then we're going to give it its value of 0 at these two endpoints. So if we look at the slope at x equals 0, and we know it's 0, again, the first two terms here, when you substitute in x equals 0, disappear. And so we also find that c is 0. So we could actually get rid of this part up here. That's helpful. And then p prime of x equals L is equal to 3a L squared plus 2bl equals 0. Because I don't have that third term of c anymore, because I already know it's 0. Now what this will do is it lets me, I know 3a squared is equal to minus 2bl. I can actually solve for a in terms of b. And that will get rid of one of my variables. And so I can take this and put it up here for a, and then I could figure out what b is. And so I'm going to do that in the next slide. Oops, sorry. So I had written that p so I have, well, okay, so I have, what did I learn so far? I hate when I have this screen. A is minus 2b over 3l. And so far I know p of x is equal to ax cubed plus bx squared. Because remember, I found c and d were 0. So now p at x equals 0 was equal to 0. Oh, that's not useful, sorry. We found that p when x was equal to L was equal to h. So I got ax cubed plus bx squared, and I'm going to let x equal L because now I'm spacing out. But I can substitute in for a, so I'm going to have h is equal to minus 2b over 3l, because that's what my a was from up here, times L cubed plus BL squared. And what that's going to do, so I'm going to be able to write that, I can combine that, is minus 2B L squared over 3 plus BL squared is equal to BL squared times 1 minus 2/3 is equal to 1/3 BL squared. So H is equal to 1/3 BL squared. So B is equal to 3H over L squared. So now, where I am right now is I have P of x is equal to minus 2b over 3l times x squared, x cubed, plus 3h l squared times x squared. So this is, remember, this is what I found A was, and this is what I found B was. But here's a B, and I have to substitute that. So I get minus 2/3 over L times 3h L squared x cubed plus 3h L squared x squared. So my P of x ends up to be minus 2h over L squared x cubed plus 3h over L squared x squared. So all I did in this first part, this is just kind of like really getting started, to be honest, is I used the conditions that they told us at the beginning of the problem to figure out what all my constants were so that I could write the curve, which is a cubic, in terms of all the things that I was given. I had to only write it in terms of h and L, and if I needed to, V. And this is what I have. And so that took a long time. And so then what I have to do is next work with this expression and use the information about velocity and acceleration. And that's where that chain rule is going to come into play. So if we go, I'm going to rewrite this. P of x is equal to minus 2h over L cubed x cubed plus 3h L squared x squared. Now P is just your y. And so we already know that dx dt is equal to minus v. That's what I said at the beginning. When we do the acceleration, we have to, the acceleration is in the y direction and it's the second derivative of y with respect to time. But the problem is that this is y as a function of x. So when we take the derivative of y, which is a function of x with respect to time, we have to use the chain rule, and we take the derivative of y with respect to x and then multiply it by dx dt. And the dx dt is just minus v. And then we're going to have to do that again. Take the second derivative again. And so we're going to have to take the derivative of this, do the chain rule, and do it again. I'm going to stop now because this is kind of long, but I'll do a more thorough job tonight, later tonight, but this could get you started. All right, so I wanted to kind of finish up this problem for, in case you wanted to take a look at it. I think what you can do is you'll work on it and you can just use this to check your algebra and make sure you're on track so that you don't waste a lot of time. So just to kind of rehash, the problem is that this airplane is basically it starts up here. It has a constant horizontal velocity. The horizontal velocity is the derivative of x with respect to time. It's a distance L away from where it's going to land, and it has an altitude of h. V, h, and L are all things that we know, even though we don't have a number for them. We should think of them as things that we know, like their numbers. We are told that the vertical acceleration can't be any bigger than this value k, and that's one of the things we have to figure out is what k is. They're telling you that this green curve, which is the path that it takes, is a cubic. And so the first thing is you're just given this really just general way to write the function. And basically, you're using what the information is that they gave you to figure out what A, B, C, and D are. So the things that they tell you, or the things that you know, is when x is equal to L, the y value, which is also P, is equal to the altitude, which is H. So that's right here. And when x equals 0, the y is 0. That's right here. The other things that they're telling us is that the slope of the graph is 0 at x equals L and at x equals 0. That's these two terms right here, those two conditions. So the slope is 0 at those two locations. The slope is the derivative. If we use this first condition and plug in x equals 0, the first three terms disappear and all we're left with is d. So we actually learn that d is 0. And if we're smart, we go down here to look at the slope at x equals 0. When we take the derivative, we get 3ax squared plus 2bx plus c. If we evaluate that at x equals 0, and we know that the slope is 0, or that derivative is 0 there, we also find out that c is 0. So things are looking up because we've gotten rid of two of our terms. This goes away and this goes away. They're both 0. Now to find a and b, we use the other two conditions, that P is at x equals L is equal to H. And so if we plug in x equals L, we get this expression right here. That doesn't really look that helpful, so we'll come back to that. But if we do the derivative at x equals 0, at x equals L, and that's 0, we actually can find a relationship between A and B. So we're going to solve for A in terms of B, and we get minus 2/3 B over L. And now if we take that value for A, we can put it back up into this expression, and then we come down here, and we can actually then simplify this. Remember, H is something we know, and we can actually solve for B. So now we know what A and B are. Oh, I forgot, I got to substitute in for B. We get A is minus 2B over 3L x cubed plus 3H over L squared. I mistakenly said that's for the rest of the problem, but we're going to have to simplify that just a little bit. So I get minus 2B over, let's try to do this. Oh no, I totally messed it up. Shoot. All right. Sorry. All right, I'm going to have to ask you to figure it out, but I had an expression, I still had B in it, but once we get rid of A and B, we should find that this is what our expression looks like. This is what our P of X looks like. Now this is also Y. P of X is like the Y in the graph. Now there's two things that we were told, now we're going to be using them. We know that dx dt is equal to minus V. That's because the airplane was going to the left, and that's the negative direction. Dx dt is just the definition of velocity. The y acceleration is the second derivative of y with respect to time. And we're told that that's less than or equal to k. Now, this is what we're after, but to get that, the first thing we have to do is take the y derivative, take the derivative of this with respect to time, dy dt. The problem is that we actually have y as a function of x, so we're going to have to use the chain rule. So we'll first take the derivative with respect to x, and then we multiply it by dx dt. Again, I wrote dp, but remember that's also y. And then dx dt is just minus v. So let's look at this expression up here and take its derivative with respect to x. And so we get minus 2h over L cubed times 2x squared, and then we write dx dt. And then we have plus 3h over L squared times 2x dx dt. And so we get I should add a 3 here, sorry. Minus 6h over L cubed times x squared times minus v plus 3h, times 2x over L squared times minus v equals 6h v x squared over L cubed minus 6hvx over L squared. So that's my dy dt. Now I got to take the derivative again, and I'm going to be doing the chain rule again. So for the first term I get 6hv times 2x over L cubed times dx dt minus 6hv over L squared dx dt. So that's 12hvx over L cubed times minus v minus 6hv squared and another negative sign over L squared. All right, so that is our expression for our acceleration. I'm going to write that on the next page. So I get minus 12h v squared x over L cubed plus 6h v squared over L squared. Now, we were told that the biggest this could be, it had to be less than or equal to k. And we have to figure out, well, where would that happen? That would actually happen right when it starts descending. And so the biggest AY is when x equals to L. So let's look at that. The acceleration at x equals L is equal to minus 12h v squared L over L squared plus 6h v squared over L squared. And that's less than or equal to k. Sorry, this is a third. Minus 12h v squared over L squared plus 6h v squared over L squared. Now, the reason it's negative is because it's downward, and so we can just look at the magnitude of it. And we can solve for, we're going to solve for L. Sorry. Well, this is what we were looking for. Sorry. That's one of the conditions we were trying to show was true, and we did it. And then the last part of it is just looking at a numerical situation. If K is 860 miles per hour squared, and your height is 35,000 feet, and your velocity is 300 miles per hour, then it's basically saying, what is L? We can basically look at this and solve for L because we're just being told what these values are. You have to have all your units right. So you need to, let's just put everything in miles and hours. It's kind of unconventional, but it will be simpler. And so we have 5,280 feet is 1 mile. And so we'll change that. And then we can rearrange this. L squared is greater than or equal to 6hv squared over K. And so L would be the square root of that. And then literally we're going to plug in all our values and solve for L. You should get 64.5 miles. All right? And so that's the end of the story. Hope it helps. Oops, solve it.